The purpose of this video clip is to apply conservation of energy in analyzing motions of systems of connected objects, such as an Atwood's machine. All right, we're going to take a look at an example of two masses, M1 and M2, that are both 1 kilogram attached to a pulley, or attached by a string about a pulley, as shown on a 30-degree frictionless incline. You're asked to determine the total kinetic energy of the system after 3 seconds. Now, there are many ways to go about problem solving here. I find that the most effective, the shortest way, would be to use the work energy theorem. But let's start by looking at these two masses, and let's consider what they're going through and what's their motion going to be. Should look kind of familiar from the forces unit. And I say whenever you can see a shortcut, you should take it if you know what you're doing. And a shortcut I see immediately is that this really is a one-dimensional problem if you consider the contour of this wedge as the one direction that this could possibly go, and you can't really jump off of that wedge. And the other thing is the two masses are connected by this string, and if we add the two masses together as if they're one object, that one object will accelerate about the curved, funny contours of our silly coordinate system. But we do that to save ourselves time. And let's just go about solving the rest of the problem now that we have that idea of a shortcut in mind. So we're going to draw our free body diagram here of the forces acting on the block. Of course, there's going to be a normal force, and looks like we have tension. You know, I'm going to draw these all in blue. Blue's taken. I'll take green, so that way they come off the picture a little bit. So that's going to be gravity, M2G. That's normal force. And then this will be tension. Now I'll do the same thing over here. That's going to have gravity M1G. It's going to have tension upwards. And that's about it. There's no friction. It's frictionless. So in our coordinate system that we've chosen, let's consider that that we know, since the masses are the same, that it's going to favor this direction. So let's call that direction the positive direction. And also, again, I'm going to reiterate that this is going to be a 1D problem, because if you think about it, the component of gravity on M2 has to cancel out with the normal force. So you're only left with the component of M2G that's along the surface of the ramp, and we'll call that M2G sine of 30. Alright, then when you do your vector addition on everything, the entire system, so all of their counterclockwise forces we're calling positive, so I'll start here with M2G is a positive number, sorry, M1G, and then we've got tension as a negative number. I'm going to subtract it, but then I keep going around the horn and I find tension is also a positive vector, so plus T, so they're going to cancel, and then the direction of this component is counterclockwise, so I'm going to have to subtract M2G sine of 30. Running out of room there. So in the end, I've got F net equals, so M1G minus M2G sine of 30. Now I can simplify that by saying M1 minus M2 divided by 2, where the G's factor out. So all of that times G. Sine of 30 is a half. I can do that. So that's my net force. And we know that net force is equal to m times A. So keep that in mind. We'll come back to that later. And now let's go back up to the rest of the problem. Total kinetic energy. Well, total kinetic energy, if it starts at rest, would really just be the final kinetic energy after 3 seconds. Yeah, this is the simplest way. Starting to doubt that. I said that at the beginning. But we know that, I'm going to apply the work energy here. So we know that the net work done on the system is going to equal the change in kinetic energy, which we talked about as being equal to the final kinetic energy minus the initial kinetic energy, which started out at 0 anyway. So if we want to find the final kinetic energy, we really should find what work done is happening over 3 seconds. Well, we know that work net, this thing right here, is going to be F net times d cosine of the angle between the work and the displacement here is just 1, so we don't have to worry about that. And we had an expression for F net, so that F net was m1 minus half of m2 all times g. Now that's just F net. Make that all green so that sort of stands out. The distance traveled, we don't really know the distance traveled, but we do know that since we're accelerating and we start from rest, that's got to abide by the kinematic formula. Displacement equals 1/2 at squared, and they gave us time, right? 3 seconds. And then that should give us our answer. We just have to do some algebra on it. So all of that equals the final kinetic energy. Alright, now what is A? If we go back to the lower right-hand corner of the page here, if we divided our F net, which is m1 minus m2 divided by 2 all times g, if we divided that by the total mass, that should give us A. So I could write A equals m1 minus m2 divided by 2 all times g divided by the total mass of m1 plus m2. So then we substitute that in, and that'll be lovely. And that gives us total kinetic energy of, I believe it's 216 joules. I might be wrong, that's just going off of memory. Okay, you try one. So you've got a 1 kilogram mass, we'll call it M2, raised 40 centimeters by dropping a 10 kilogram package in the systems shown. Again, we're working off of page 11 in your practice packet. Give this one a try and then check your work when you're done.